Hey, welcome back to Fat Mama Physics. In this video, it is part of the 3 videos on power and efficiency. In this video, we will specifically tackle efficiency. Here, there's a few things I want you to know before we move on. When we talked about conservation of energy, there were times when energy was lost to our system, say in the form of friction or thermal energy. Once the energy is gone from our system, it is no longer useful to us. It's gone to waste. So if our system is more efficient, less of that energy will go to waste, thermal, or other energies that we cannot use. We like to draw a flow chart to illustrate where that energy tends to go. In fact, I used it in a previous video before, but there's a specific name to that diagram. It's called a Sankey diagram. What's interesting about a Sankey diagram is that these arrows, the width of these arrows, is directly proportional to the amount of energy at that point of the energy flow. So here I have an example. We start off, there's a coal power plant where coal is being converted to electrical energy. We have a lot of it going into waste. So we start off with 100% of the energy going in, 70% of it gets lost. Notice there's this sum of thickness of the arrow leaving this 100%, and then only 30%, which is a skinny part of that arrow, is left behind, getting transformed into useful electrical energy for us. There's a few words that I want you to be aware of. The energy that goes into our system, we call that energy input. The wasted energy here is just exactly what you see in the diagram, but it's also useful to know. This is the wasted energy, and then the amount of energy that comes out of our system that we can use, it is useful to us, we call that energy output. So if you take a look at this diagram, we see that 100% is equal to 70% plus 30%, which is exactly the energy input is equal to our wasted energy plus our energy output. And I just used the letter E for energy instead. So in fact, we can use these numbers or this idea here to talk about efficiency. Whenever we have efficiency, it means we have a percentage. So don't forget, if you do divide two things together, you do need to multiply by 100%. How do we calculate the efficiency of our system? The efficiency of our system is our energy output over our energy input. Now, if we use this diagram as an example, the energy input we have is 100%. The energy output that is useful to us is 30%. So if we have 30 over 100 times 100%, that gives us, well, 30%, which is really obvious in the diagram already. But if you have a really efficient system, the more energy output you're going to get per energy input. So imagine you go in with 100 units of energy. If you get, say, 100 energy units out, then you would have a 100% efficient system, which in the real world is not possible. But what absolutely cannot happen is that you get more energy output than your energy input. That just doesn't make sense. It violates the conservation of energy, which means energy cannot be created out of nowhere, okay? So that's efficiency for you. A lot of our systems are motors, and nowadays for, say, electrical cars, get up to 30 to 50, and of course, the more efficient our system, the better, right? The more money we save. So that's efficiency. Now, the other thing you can use instead of energy is, in fact, power. So this would be power output over power input. You might be thinking, well, why can't we use power? Isn't it just energy? Don't forget, when we talk about power, that's the amount of change in energy per unit of time. So if I just divided the top here by the time and the bottom here by time, I've done nothing to the rate of proportion for this fraction over here. So if I do divide my energy by time, I do get power. So if I divide the top and bottom by the same thing, that is okay. And which may help you to do other problems with involved power instead of energy. So knowing these equations, we can now tackle some examples. I'm going to do example 5, and you're going to do example 6. You might be wondering why example 1 is above there, because I'm going to use example 1 again. Example 5. using the Serenity ship in example 1, which is right there, if Serenity's generators are 33% efficient, calculate how much fuel energy was needed in the 5 seconds. So here we have an efficiency, and what we do want is the fuel. It looks like we are looking at the fuel that goes into the spaceship, so it's going into our system that is some sort of energy input. That's what we want to find. And I'm going to write E in as energy input is what we want. To calculate for the energy input, we are going to need the energy output since we have the efficiency of our system. And to find the energy output, we have to look at example 1 again. So it seems like in example 1, the spaceship is accelerating from 20 kilometers per hour to 100 kilometers per hour. And that's a change in kinetic energy, which then we need to calculate that. That's going to be the energy output, is that change in kinetic energy. So let's calculate change in kinetic energy first from example 1. If you watched the previous video before, you probably have an idea how to do it. So let's do it together. And we need the mass, which is right there, 54,000 kilograms. We have the initial speed, we have the final speed, and which we can put into our change in kinetic energy equation. But don't forget, we got to convert these to meters per seconds. So I'm going to do that really quickly actually inside my equation. And I also told us a quick way to doing that is to converting kilometers per hour to meter per second is to simply divide it by 3.6, which then I'm going to do that in-house in our equation, so to save some space because I'm running low on space. So the final velocity is speed is going to be 100 kilometers per hour, and I'm going to be dividing that by 3.6 to convert that to meters per seconds. And if you don't remember, I'll refer to the last video exam, power efficiency number 1, to look into example 1 how I did that. So I'm going to put that in, square it, and subtract by the initial kinetic energy, in which the speed here is 20 kilometers per hour, divided by 3.6, and the whole thing squared. Putting that into our calculator, I get, and that's a whooping 20 million joules. Okay, so now I have the energy output. We can now find the energy input by using this 33% efficiency here. So based off our equation, we got the efficiency, which is a percentage, 33% is equal to our energy output divided by our energy input times 100%. First things first, let's convert this percentage to a decimal place by dividing both sides by 100. Okay, and we want the energy input, so we're going to solve for energy input by first multiplying it to both sides of the equation, and then dividing both sides of the equation by 0.33 to get the energy input to one side of the equation. I get the energy input as the energy output divided by 0.33. Which is the 20 million divided by 0.33, in which I am going to get 60.6 million. Rounding off to 2 sig figs, that's just going to be 6.1 times 10 to the power of 7 joules. Lot of money there, very jewelry. Okay, sorry. So that is how you can use how you would apply efficiency. So now we have B and C. B is how much fuel energy was converted into wasted energy. Oh my goodness. So what that is asking for is how much of this initial energy input is wasted. So the W, the EW, the E waste, okay? So how to find the wasted energy is we need the energy input, and we need to know the percentage of energy that goes into wasted energy. We know the useful energy is 33%, so the wasted energy is just 100% minus the 33%, giving us 67% of the energy input being wasted. So in fact, we can get 67% of the energy input which is what we just calculated was what, 60.6 million joules. So we can do a multiplication here, which then we do 0.67 times 6.06, and I believe that was repeating, times 10 to the power of 7 joules. So keeping all our sig figs. This is just like when you go to the store and you're trying to find how much discount you get off of, I don't know, bread or something. So let's do that. Hey, we got the value stored there, so we can just go ahead and solve for that. So I'm just going to multiply by 0.67, and we get 4.06 repeated times 10 to the power of 7 joules. If I count the zeros, should be 1, 2, 3, 4, 5, 6, 7 for 4.0. Okay, and that rounds to 2 sig figs, 4.1 times 10 to the power of 7 joules. Okay, and I can actually check, do a quick estimation here. 67% of about 6 million is roughly about 2/3 of that amount. 40 million sounds about right. Okay, so this is something you can do a check at the end just to make sure you have the right number. If I got 10 to the power of 6 or 5, then I know something's definitely wrong. Okay. And last but not least, C, the fuel power input. Okay, so before we found the fuel energy that we need to kickstart the engines, but this time we want to convert that to the power input. To find power, we know that it is just the energy divided by time. So if we have the input energy, we have the time is 5 seconds, we can calculate power input. Energy input is, we calculated that in question A, which we found to be 60-ish million here. So 6.06 times 10 to the power of 7, which we will use right now, and divided by the 5 seconds for our time, we get 12 repeated, so that is 12 million. And rounded up to 2 sig figs, that's 12 million exactly. So 1.2 times 10 to the power of 7 watts. Okay, and here we go. Here is the question, okay? So notice that we've been circulating a few values, including energy input, energy output, power input, power output, and as well as the efficiency of the system. And you can see how these are all related to one another through either the power equation or the efficiency equation. And the key thing in doing these problems is to making sure you can identify which is which one, when you calculate it, is which. If you know which one you have, you know how to find the other ones, okay? So hopefully this question will give you some tools to help you do the next example, example 6, in which, oh hey, it is a recap on example 2. So let's read this together. Example 6, if the space elevator thrust engine, example 2, uses a 9,400 kilowatt motor, calculate the efficiency of the motor, amount of energy wasted in the 2 seconds, and the energy input in the motor for the 2 seconds. So you got a new number here, which is this guy. It looks like it's some sort of power because it's got a watt in there. Whenever you see the a K in front of the units, that means kilo. And kilo means 1,000. So that is 9,400. And then the kilo gives you an extra 3 zeros, 1, 2, 3. So that gives you 9,400,000 watts in total, okay? And whenever you're talking about a motor, that's usually referring to how much energy or how much power is going into your system in order for it to, in this case, move your elevator upwards. So here you have, and if you don't already know, if you're unsure, this is your power input. So you have power input to begin with. I'm going to give you a chance to try this problem. So it's a good time to pause. Now I'm going to do the solutions on Fast Play. Alright, to calculate the efficiency of our system in percentage, we need the power output divided by power input. To find the power input, we need to go back to example 2, in which the power output was change in potential energy over time. The initial potential energy was 0, so then we just can find the final potential energy divided by time, and we get same thing we found in example 2 in watts. We can then put that into our equation. The power input is in the question, given in the question itself, so dividing the 2 multiplying by 100% gives us 52.9, which rounds to 53%. Now, to find the amount of energy wasted, we need to convert the 53% into, we need to find the percent of energy wasted, which is 100% minus 53%, giving us roughly about 47%. And to find the amount of percent of energy that's wasted, we need to multiply that percentage by the energy input, but we don't have the energy input right now. To find the energy input, we need to look at the power input. To get the energy input from power, you just need to multiply it by time to get energy input. So then we have the energy input. We can then multiply it by 0.47 to get the amount of energy that is wasted. So then that's 0.47 as a decimal multiplied power input multiplied by the time, giving us about 8.9 times 10 to the power of 6 joules. Next up, we need to find the energy input for the motor, and hey, I think we had that in the previous question already, which is just power input multiplied by the time. So then just putting that one into our calculator, we get 18 million, which is 1.9 times 10 to the power of 7 joules, rounded to 2 sig figs. Okay, and here are the solutions. It looks like that I asked for slightly different things than in the previous question, but if you apply the same equations and the same set of skills, hopefully you will be able to get what we have gone over here, alright? So, hopefully you learned something from this video that you can use later on. I thank you for watching, good luck, and Fan Mama Physics signing out!